Okay. Good evening, everybody. Today we are going to learn the sliding mode control. So first, we just understand what is sliding mode control. Basically, the sliding mode control, it's a model-free adaptive control with variable control structure which can provide robust control and have better disturbance rejection capability. Because when you want very tightly control over the output parameters of a plant, definitely you should have the feedback and there should be one controller. But conventionally it is very oftenly we will use PID or PI. But the thing is, to obtain a high performance dynamic response of the plant, you need to understand the dynamics of the entire plant. For that you need the identification, the system identification. Once you identify the system, then it is very easy to linearize the system either over the entire range or piecewise, and then it can be tuned very easily. But in some system plants, mainly in power electronics or some robotics, this kind of precise control means not precise, kind of variable responsive system. The main difficulties is the control variables. They can change time to time. So that time the design of controller will be very difficult. So for that kind of application, this sliding mode control is very suitable one. In this control, basically the plant is forced to track or slide along a predefined path, that is the desired response I need to obtain. Say for a motor control application, I want a particular torque profile to maintain. This can be obtained by continuous changing of control variables. Okay, likewise you can take one example of MPPT where always we want to fix the maximum power to be delivered to the load by changing the impedance between the source and load by matching, which will infer the maximum power transfer theorem. That means by changing the duty cycle of the DC to DC converter, we will always make the input and output impedance as a complex conjugate, so that the maximum power can be transferred at the output. So likewise SMC, this sliding mode control, also one of the control technique which will continuously change the control parameters, and it will provide a robust control which is irrespective of the main plant dynamics. Okay, so why we want to use it? As I told earlier, for any digital controller like PI or PID, unless otherwise you are able to linearize the system, you are able to linearize the small signal model of the plant, you cannot tune it properly to obtain the high performance dynamic response of the system. But in sliding mode control can be applicable to nonlinear plant also. Okay, and the control structure is entirely independent on the plant parameter variation and also the output disturbance. Likewise, if you can take an example of vector control of asynchronous induction machine, so the quadrature loop tuning is quite difficult, because the natural frequency of outer loop controller, that is the speed controller, and the inner loop torque controller, they are in different phase plane. So this kind of things can be achievable with very high performance dynamic response by the application of sliding mode control. So this lecture series I am making first the very basic things, basic derivations of that, then the physical interpretation of this sliding mode control, and after that we will simulate it using some softwares, and finally we will implement that control using a non-isolated DC to DC converter or a multi-level inverter. How to in microcontroller and the hardware how to implement it. So there will be 3 or 4 lectures related to that. So application of the sliding mode control is extensively used nowadays in servo, induction and asynchronous and synchronous motor drives, power electronic control. Now we are going to the basic structure. So here I have considered one second order undamped system with variable plant gain K, and from the structure you can understand it is highly unstable. Here we have used one positive and one negative feedback path inside the digital controller. Even though the system is unstable, but we can make it stable by continuous switching over from positive to negative and negative to positive. Okay, and this control structure, when we will be finally deriving the mechanism, we will understand it is independent of the plant gain K. Okay, so now here we are the excitation we have used as a unit step signal R, which is R, and this x1 is the error, and there is a feedback path of unit gain, and C is the output. Okay, so now from here very few notations I have used. So S in Laplace domain implies derivation at time domain, and 1 by S in Laplace domain is implies integration at time domain. So now if you consider the earlier figure, so here this x1 is equal to R minus C. So that's why I written x1 is equal to R minus C, and similarly likewise R is equal R minus x1 is equal to C. If I now differentiate, so this is the things. So now again if I differentiate, that means S square x1 is equal to minus S square C. That is nothing but d2 x1 by dt square is equal to minus d2 c by dt square. Okay, so this is the thing. So now from the figure, for negative feedback, the output C is nothing but x1 into K by S square. You see this one. So this output C is equal to here this x1 into this plant. So I have written this one only. Now this implies S square into C is equal to Kx1, which is nothing but d2c by dt square is equal to Kx1. Now if you consider the equation 1 where S square x1 is equal to minus S square C, and here that is S square C is equal to Kx1, and if you combine this equation 1 and 2, now you are getting finally this one, which is a second order differential equation with 0, there is no excitation. That means d2x1 by dt square plus kx1 is equal to 0. So there will be only complementary function part, there will be no particular integral. So if you solve this second order differential equation, so you will get a solution of like this: a sine root over kt plus phi, where k and t are two arbitrary constant. Now x2, I am defining one variable x2, which is nothing but the derivative of this x1, and which is nothing but this one. This is very simple differentiation. Okay, so this is sin theta become cos theta, and root k it's coming out. Okay, now this x1 by a is equal to sine of some theta. Let us consider this part as theta. So x1 by a is equal to sine theta, and x2 by root k is equal to cos theta. Now both if you square, then it will come x square by a square plus x2 square by k a square is equal to 1, because sine square plus cos theta is equal to 1, which is the equation of ellipse. So from there we will, so this is the phase plane plot. This is the phase plane plot when we are considering the system with positive feedback. Okay, so first one we have used for this is for negative feedback. So now we will be doing the same for negative feedback, for positive feedback. So positive feedback also same, only the things here only instead of minus it will be plus. Okay, so the same way. So now if I combining the equation 1 and this 5, so it is become like this. So it is also a second order differential equation, which is nothing but d2x1 by dt square minus kx1 is equal to 0. So now if you solve this equation, now if you solve this equation, so what will happen? If you solve this equation, so you will get a solution of like that: x1 is equal to b1 e to the power kt plus b2 into e to the power minus root kt. And simply if you differentiate, this x2 is a variable. I'll tell you why I am differentiating, that will come later. So this x2 is a variable I have defined, which is nothing but the first derivative of x1, which is nothing but this one. Okay, so similarly here again, if you take this, if you square both the terms, both the x1 and x2, if you square both the side, and if you substitute, if you eliminate the exponential part, so the equation will convert this x1 square by 4b1 b2 minus x2 square by 4k b1 b2 is equal to 1, which is a hyperbola. So from this explanation, this is the first lecture. So from there we have understood when the system is in negative feedback, when the system will be working, when the control system is working with the negative feedback portion of the controller, so the phase plane will locus through a ellipse. And when we will use the positive feedback, so this is the negative feedback, and for the positive feedback this is the equation. So for the positive feedback, this phase plane will be moving with these two variable, these two variables x1 and x2 will be moving in a phase plane following a hyperabolic path. So this is the end of first lecture. Then in the second lecture we will understand how this predefined trajectory, means how we need to define the desired control trajectory, and by controlling these two variables x1 and by controlling this constant b1, b2, k and a, all these things, that means basically it is nothing but by controlling this x1 and x2, how we will follow the predefined trajectory to obtain the desired response of the system. Okay, thank you so much.